Welcome to the video on the battery recycling. In this session, I'll be talking about why we need battery recycling, what are the methods for recycling, along with their advantages and disadvantages, and evaluate if it is worth it. Throughout today's discussion, I'll be focusing on the lithium-ion battery recycling as it is dominating the battery market and play a very crucial role in the renewable energy cycle. With increasing concern for mitigating climate change, the demands for the electric vehicles are going high. And as a result, the lithium ion battery plays a very important role due to its high energy density. Among all energy storage solutions, currently the lithium ion battery covers about 37%, and it is going to increase further. Statistical data shows that about 1.2 million tons of lithium-ion batteries entered the global market in 2019, and projections indicate a significant increase over 12.7 million tons by 2030. Now, due to eventual aging of the first generation of the EV lithium-ion batteries, they are ready to be recycled. Therefore, the global lithium ion battery recycling industry is expanding significantly as governments and companies respond to the rising demand. But of course, the first question appears to be, why should we recycle lithium ion batteries? Here, in the good old periodic table, the highlighted elements are used in lithium ion batteries with different cathode anode chemistries. For example, the cathodes have the lithium, transition metals, phosphorus, sulfur, and oxygen. The anodes have silicon, carbon, etc., whereas the electrolyte mostly consists of lithium, carbon, and oxygen. Aluminium and copper foils are used as the current collectors. The casing is mostly made up of insulating plastics, metals like iron. In the table at the right hand side, you can see the abundance of these elements in the Earth's crust. Now, if you look closely in this table, many of the transition metal elements as well as lithium have very low abundance. The total lithium present in the Earth's crust is about 105 million tons. However, if we need to attain the environmental goal of meeting the net zero, it would require about 905 million tons, which is impossible with the single use of lithium ion batteries. Besides, due to the low abundance and geopolitical issues, the cost of cathode materials accounts for more than half of the total cost of the lithium ion battery components. One of the ways that we can address these issues is by recycling the lithium ion batteries. This can potentially lead to a 28% reduction in the raw material demand. Therefore, utilizing the recycled materials not only reduces the battery production cost, but also reduces the overall energy requirement for battery manufacturing at least by 48%. It can reduce the carbon emission by 2.7 to 4.6 kilogram of carbon dioxide equivalent. Currently, the global annual recycling capacity is about 1.6 million tons, which is much lower than the market demands. Well, now let's see how the lithium ion batteries can be recycled. To understand the lithium ion battery recycling process, first we need to revise the configuration of the lithium ion battery. Each battery has a cathode coated on an aluminum foil, an anode coated on a copper foil, and these two electrodes are separated by an electrolyte soaked separator. These active parts are encapsulated inside a plastic and metal casing. For the recycling process, first the battery has to be discharged, then disassembled into different parts. This is followed by the physical separation and materials recovery. Keep in mind that many of these processes are also widely used for the recycle of other types of battery. In the very first step, the discharge process is done either via external discharge or using a salt solution process. This process is done for avoiding the risk or the fire or smoking in the following steps. For the smaller portable batteries, an external short circuit is done under controlled condition. However, for the larger batteries, this could be dangerous. Therefore, they are merged into a salt solution which slowly neutralizes the battery. After this, the battery is disassembled using immersion, gas blanket, and high airflow comminution techniques. This makes the next step much easier, where the different physical parts of the battery such as the plastic, the metal casing, the separator membrane, electrolyte, and the electrodes are separated from each other. Now, as the different parts are separated, the active component are used for material recovery. This step is done by either hydrometallurgy, pyrometallurgy, biometallurgy, or direct regeneration process. These can give back the precursor salts or materials for the electrodes as well as the current collector metals. Now let's understand what happens under these processes. The hydrometallurgy process is based on the chemistry of the solubility. Here the materials are dissolved and precipitated back using different acids, bases, and additive chemicals. This results in very high purity of the element. In the pyrometallurgical process, the materials are directly heated into a high temperature smelting furnace. This leads to incineration of materials such as plastics, organic matter, and graphite. The elevated temperatures help the metal species reduction, including the cobalt, nickel, and copper, generating alloys by reducing agents such as aluminum foil, graphite, and charcoal. Meanwhile, lithium, manganese, and aluminum are entertained within the slag. In the biometallurgy process, the microorganisms are used to extract metals from the recycling sources. Here, the microorganisms such as bacteria, fungi, archaea are used to dissolve metal oxide and carbonates. This could be considered as a branch of the hydrometallurgy process. The direct regeneration process involves replenishing the lithium in the retired cathode through chemical and physical processes and has significant advantages compared to the previous methods. All of these recycling processes have certain advantages as well as disadvantages. Now, coming to the hydrometallurgy process, it is a highly mature technique and has a low energy consumption. It can selectively extract valuable metals with a very high recovery rate. However, many a times, the separation process and the recovery step are quite complicated. It produces very large amount of alkaline or acidic wastewaters, which is concerning for the environment, particularly for the water life. The process of pyrometallurgy process is quite straightforward and highly productive, so it is good for large-scale production. On the other hand, it consumes a lot of energy to heat up the materials to the smelting temperature. The lithium we get from here needs to be further recovered. Now coming to the biometallurgical process, it's one of the most environmentally benign recycling technology. It can also be combined with other processes. However, this process is industrially limited due to the long bacterial culture cycles as well as rising labor cost. The direct regeneration method is beneficial due to low energy consumption, simple processing, and low pollution. Although direct regeneration of the cathode materials is currently limited due to laboratory scale, it may be used on a large scale in industry in the future. Now, looking at the advantages and disadvantages of all these different processes, there is a trend moving from the pyrometallurgical process to a combined process of the mechanical treatment and hydrometallurgy. It is expected that the hydrometallurgical process will remain dominant for quite a long time to come. Now, to summarize, we have discussed the benefit of lithium-ion battery recycling in terms of environmental impact and economic benefit and the methods involved in these processes. With this knowledge, we also need to remember that to proceed towards scalability as well as environmental sustainability, we need to develop new recycling routes or combining them with better recovery efficiency.